taking. Okay. Yeah, thank you all for coming today. Really appreciate the turnout. Hopefully you enjoy the pastries. So I'm going to keep walking you through the journey of my research here and into this area of autonomous earth moving and more specifically terrain shaping. So I want to start out with a few definitions. Maybe? Yeah, so in autonomous terrain shaping, what I'm really meaning here is the sense of taking some starting terrain, something like this, a flat area, and then through the use of heavy earth moving equipment, bulldozers, excavators, those types of things, to transform the terrain to a new shape for some purpose. In this case, they're performing multiple sequences of these kind of earth moving cycles, the bulldozers making a push, building up this berm, and in order to end up with something like a pond in this case. This is a challenging problem to automate for a number of different reasons. I'm going to try and highlight a few of those. For one, the environment is quite complex. So we only have partial observability of the system at any one point in time. We can't see through the ground very well. So we don't know if there's rocks that are buried. Soil conditions vary spatially, both with depth and kind of the extent. And the interaction between a bulldozer, for example, and the terrain is quite complex. These are very complex mechanical systems with nonlinear hydraulics. And then the process of blade engaging soil is actually very difficult to model physically as well. And the tasks themselves are somewhat long horizon in nature. And the other thing is, because you're trying to perform multiple earth moving cycles at a time in order to achieve some sort of desired objective. And it's expensive to experiment on these platforms, right? So, it takes time to have a site to be able to perform these experiments. Simulation is difficult. So overall, it's costly. And so how do operators actually solve this problem? Well, what they do is they use all of their senses. So as you're sitting in the cab, the vehicle moves. So you can kind of get a sense for when the blade is engaging the terrain. You can listen to the sound of the engine in order to determine how difficult it is to dig in a given region. And importantly, using your vision in order to kind of see the changing soil conditions and the change in the terrain shape and that kind of thing. So what I want to do here is kind of motivate the fact, kind of make an observation that soil conditions really affect this earth moving process. And this is a number of reasons. So when your blade is engaging the ground, the soil conditions themselves change the force that is required in order to shear that soil. So the system has to exert more torque on the tracks to cut the soil. And additionally, what that means is that it affects the feasibility of a given plan. So if you just have some sort of kinematically planned trajectory, this may not actually be achievable because of the forces required to execute this operation. So, and additionally, if it's not achievable, then that changes the amount of material that can accumulate in a system. So this affects planning. So in this case, we thought we were going to get this much soil. We actually got that much. So you can see how that can accumulate and cause problems when you're performing these longer horizon tasks. Performing a second cut with a soil ignorant system that's not really paying attention to the soil conditions in any way. You may make another plan here to try and cut off the top of this little hill. But what happens when you go to execute that is that, kind of you create some sort of gouging of the terrain. And this can cause issues because it makes it significantly more difficult as the vehicle drives over this in order to control the height of the blade, for example. And again, this is inefficient and it can cause problems in the earth moving process. What I'm interested in working towards here is developing a soil-aware earth moving system and developing a soil-aware planner of some sort. And the idea here would be is that, if we have some idea of the soil conditions from that first pass of operating in the terrain, we can say, actually, we can start back a little bit further in our cut. We can then do a better job of accumulating enough material, and we're maybe a little less aggressive in this region than we think is higher density soils. So things get even more difficult if you start thinking about buried objects, for example, rocks and things where it's physically impossible to actually make a cut through that region. You're not only making small cuts, you can't make a cut there at all, perhaps. So this is all to motivate the need for soil property estimation and for additionally mapping. So since these things vary spatially, we want to track them in some way spatially. And what this can allow us to do on the back end is to do things like try and reduce the the gouging, trying to create smoother terrains, increase the efficiency of the overall system, and doing things like maybe avoiding this region where the rock was at, or alternatively, trigger some sort of separate controller that allows us to do varied object, for example. So there's been a decent amount of work in this space of earth moving. A lot of it's more on the side of development of autonomy for excavators. But there are a number of applications for autonomous earth moving specifically applied to bulldozers. So there's some work in the mining fields where you're trying to get down to pull seams and that type of thing with large earth moving equipment. Additionally, some of the applications that are really motivating this work are combat engineering, where you're wanting to do things like reduce berms so that vehicles can drive over them, do things like fill in anti-tank ditches, for example. And then, there's other applications such as space or other operations where it may be just infeasible to teleoperate, for example. So some existing autonomy is on some of these platforms from the factory now in the form of these operator assist systems, which do things like help to stabilize the movement of the blade, but are really not reasoning about the environment in any way. On the more research end of things, there are some collaborations between industry and universities. Caterpillar in Queensland is one notable one, doing things like trying to develop mathematical programming methods to plan out sequences of cuts and fills for mining operations. Additionally, there's work more on the academic side of things where people are trying to apply things like reinforcement learning algorithms in order to learn policies to perform terrain shaping operations. Where to begin a cut, where to deposit the material, that kind of thing. The thing is that all of these methods have in common is that they're pretty limited in scope. They assume very kind of limited conditions on the soil. So you're assuming things like cohesionless soil, essentially sand, that soil conditions are uniform in some manner. And this is kind of restrictive for the types of applications that we're really interested in. And what this motivates is really a need for autonomous systems to be able to adapt to these varying soil conditions. Yeah, so what I want to do here is lay out some of the goals of this work now that we've motivated the problem. And to start out, it's useful to kind of put these autonomous earth-moving systems in a conceptual architecture, this canonical architecture for autonomous terrain shaping. And so let's walk through this a little bit here. Starting at the top, we have these height map looking things. These pretty colored pictures here are indicating that over here, this is the current terrain state. So this may be representing the shape of the terrain. And then over here, maybe we have something that is a goal state, which could be an actual height map, or it could be some condition on an actual height map. So whether we want the system to be smooth, for example. And what this does is it feeds the planning system. And typically, in order to solve these long horizon problems, one of the heuristics that's used is to break things down in a hierarchical fashion. So planning of things at a high level in terms of sequences of earth moving operations at the strategic level, and then at the tactical level, planning individual pushes with a bulldozer and what trajectory needs to be taken. And then these systems output plans to a controller, and the controller is able to then follow these plans, typically in the form of some sort of kinematic trajectory of the blade in the vehicle. And this can be done in closed loop, where we're getting feedback on the state of the system. Where is the vehicle at? Where is the arm at in relation to the terrain? Those types of things. And then the hydraulic valves on the system are controlled in order to change the position of the blade and the tracks. And this requires some sort of state estimation in order to kind of estimate all these things and take measurements of the joint positions, those types of things as well. But importantly, we also need some way of estimating the environmental state. So as we're changing the terrain, we need some way of tracking how the terrain is being changed and to enable replanning in the future. So we need this environmental state estimation component. And so this consists of both mapping in 3D, but also if we're interested in doing soil aware terrain shaping, having some sort of soil property estimation built in here as well. So what I'm going to talk about today is kind of organized into three main contributions. So talking about estimating of soil strength properties. How do we actually formulate that problem? And what do we mean by soil strength properties? And how do we do it during the earth moving process? So as a system is trying to perform this terrain shaping task. Secondly, how do we build maps of the environment, and not only terrain maps, but actual maps of soil properties themselves? And then there's a number of contributions in this area of building planners and controllers in order to perform actual terrain shaping tasks, both at this kind of lower level and then more at this planning level as well. Maybe. Clicker stop functioning. There we go. Okay. So just to give a bit of an overview here, to kind of, so you can see a visual outline here of the work. A lot of the initial work that I started out with was using these kind of simplified simulation of bulldozers, moving in 2 dimensions essentially, but you could control the height of the blade. Later on, moved to more advanced simulations of a compact track loader with a blade on it. So this tracked vehicle with an arm and a blade attached. And then most recently developed and implemented some of these systems on an actual compact track loader, which we're calling the Rio RCTL. So I guess the second axis here to talk about is that we're organizing these contributions in this environmental state estimation area, and then as well as in the planning and control. So the first work is this soil property estimation method. And this is kind of formulating this problem of what do we mean by soil properties? How do we estimate them? Secondly, we'll talk about this terrain and soil property mapping. How do we actually represent these soil properties in a spatial manner? So we're tracking their position throughout the environment. And additionally, looking at model learning and control for bulldozing. So how do we kind of learn the dynamics of this process, how the terrain moves with the blade, and use that for performing some sort of earth-moving task. And finally, we're going to talk a little bit about the map-assisted terrain smoothing. So this is some actual work on the real vehicle. And I got that a little bit out of order. We're going to start talking about this model learning and predictive control for bulldozing briefly. This is actually where I started some of my initial work in this area. I was really eager to get working on a terrain shaping task to begin with, potentially oversimplifying the problem a little bit, but it provided motivation for the following work. So I will go through it briefly, but essentially here we use these simplified models in simulation of a bulldozer that you kind of see depicted over here where the blade can engage with the ground. There's no chassis, it's kind of floating and invisible. But and the basic idea here was, can we collect data from human operators as they're performing an earth-moving task like berm removal? And then can we use that to learn a model of the earth-moving dynamic itself? How does the terrain move when the blade is engaging with the ground? And what does the blade do when it stalls out? So at a high level, what we're doing here is we're observing a local or a height map that's kind of centered around the blade, representing the shape of the terrain. We're additionally observing position and velocity information of the vehicle and the blade, the chassis and the blade. And then we're recording the control actions that were taken by the human operator as well. And the objective here is to learn this function. So how do we learn the evolution of the state of the system? What does the height map look like at the next time step, given the control actions that were taken? And we're doing this in a reduced order forward model learning process. So by reduced order, I mean that we're not modeling the evolution of every pixel to pixel. We're kind of compressing things down into a lower dimensional space and then modeling the dynamics in that lower dimensional space. And there's 2 different methods that we use to test this idea. One is this dynamic mode decomposition with control, which is a method that's kind of PCA-esque for those of you that are familiar. But it essentially allows you to model these kind of high dimensional dynamical systems, things like complex fluid interactions, and approximates these very nonlinear things as lower dimensional linear systems. And it's shown to be successful in some of those domains. Additionally, the second approach that was taken is a more machine learning type approach, which is this world models-based method, which uses a variational autoencoder and a recurrent neural network in order to model the latent dynamics. And this VAE is essentially used to reduce the dimensionality of the height map. And the way these models are used is in this kind of moving horizon fashion. So we learn the model on a small amount of human operator data, and then we try and evaluate potential actions and see how that affects some sort of rewards. We want to maximize some sort of task, berm removal in this case. But we want the system to be subject to the dynamics that we have learned. So in this case, this is the reward function. We want to reduce the height of this berm, which just kind of moves along with respect to the height map. And what we do is we perform this kind of, in this case, a fairly crude optimization, but over 60 time steps or about 1 second of data, and select the actions and apply that for a short period of time before we perform a re-optimization given those new updates. And this is an example of the world model method working. It works all right, and in particular, it actually performs kind of on par with human operators, a little less good, but similarly in performance, especially given the small amount of training data. This is a promising result. It's a very sample efficient approach, and in general, that's one of the reasons that we could have went with the model learning based approach as opposed to a model free RL approach. I guess there's a lot of potential improvements in this area. Really being able to train the system online and end to end, as opposed to collecting data, then using model to make predictions and then act in the real world. If we can kind of close that loop so that we're collecting data along the way and retraining the model simultaneously, this is going to allow us to solve some of these problems with out of distribution errors that we run into. And additionally, we'd really like to move towards more realistic dynamics. And in particular, starting to think about this problem of how do we incorporate these varying soil conditions in all of this. Next, I want to talk just about that, how we can talk about, or how we can actually do estimation of soil properties. So this work was presented at International Society for Terrain Vehicle Systems in 2023. And in the title, I'm going to highlight this term in situ soil property estimation. So that just means that in this case, we want to be able to estimate soil properties as a vehicle is interacting with the terrain, as it's performing these operations. We're not requiring some separate test to be performed. It's as it's trying to do the task that it's assigned. And we're using, I'll get to it in a second, I guess, physics-infused neural networks. If we're trying to estimate soil properties, we have to have some sort of model that we're estimating the parameters of. In this case, we choose to use this thing called the fundamental equation of earthmoving, which is depicted in this figure here. It's a fairly simple model of bulldozing, of a blade interacting with the ground, but it's been used in the literature in this space for a while because it does a pretty good job of representing the physics and the forces required in order to shear the soil. So essentially what you're looking at here is this gray line indicates this is a blade looking at it, the blade in profile. And the green line is the soil surface. And then you have these circles up here indicating material that's built up on the front of the blade, so the surcharge as the bulldozing operation proceeds. And then you have this kind of wedge of material and the dotted line that is being sheared. So it's assumed that the soil kind of shears along this wedge here. And basically what we do is we assume a more Coulomb soil strength model, which I won't get into the details of, but it kind of parameterizes the physics of the underlying strength and properties of the soil. And I guess a couple of things to point out is the parameters of this model kind of be broken into two different sets of components, this theta k and theta u. Theta k being the more geometric parameters of the model. What's the blade angle with respect to the surface, the angle of the soil with respect to, or the surface inclination angle, those types of things, as well as the weight of this mass and surcharge, which is a little less geometric, but we'll talk about how we can estimate that in a second. And then the other thing is really these slope properties, this phi, c, delta, ca, and gamma, which represent the kind of physical properties of the medium. And so I guess a couple things to point out. This system kind of is quite nonlinear in these coefficients. And I'll show you some of the math just for maybe one of my clickers disobeying here. But essentially, yeah, it's fairly nonlinear. And so it's a complex equation to some extent, even though it's a simple model. But so beyond the FE, we've made a number of modifications to kind of formulate this as a probabilistic distribution as well. And the reason that we want to do that is because we're also interested in estimating the parameter uncertainty. So as you're performing the bulldozing operation, there's going to be scenarios in which you're making very shallow cuts, for example, and it's really hard to ascertain anything useful about the terrain from these kind of shallow cuts, for example. There's other configurations that result in us making it difficult to actually make any inferences about the properties themselves. And so we want to have the system that's able to spit out these values, but also tell us how certain we are in these estimates. And so we formulate this here as kind of a normal distribution, and where the FEE is used as the mean of this distribution, and then we have this variance in the force. But really what we want is we want to model the variance of the soil properties, not just the variance of the force. And so one of the tricks that we use here is to use this uncertainty propagation method in order to basically take a derivative of the FEE model with respect to the parameters in order to get these, to be able to use these sigma theta, the properties of uncertainty properties of the soil properties themselves. And we'll get into that in a second. Yeah, so I guess there's some existing work in this area. Briefly, this kind of fits under the category of inverse terra mechanics. You've got a measurement of a force. You want to invert the FEE model in order to obtain these parameter estimates. Typically, this is done by measuring the force via something like a force plate that's attached to the blade or the bucket. And then the way these systems proceed is that record data from multiple dig cycles. So most of the prior work has been in the use of excavators. And so they're requiring multiple dig cycles in the same area where you're making the assumption that the soil properties are not changing over the course of that. And then nonlinear optimization methods are used in order to find these data parameters. And typically this is only done for a subset of those 5 properties. So looking at cohesion, internal and friction, for example. So the major contributions of this work here is that this is, to my knowledge, the first known approach for bulldozers. There's other people that have used these kind of methods with a blade in sand in kind of a test bed here, but on an actual moving vehicle. This is the first known approach there. And in order to enable that, one of the things that we did is instead of requiring these 3 to 8 full dig cycles, we're just requiring 1 second history of data of the system interacting with the terrain. And this is important because the bulldozer is not stationary when it's performing these digging operations. It's moving throughout the environment. And so we want to be able to estimate these things fairly quickly. Additionally, in order to enable that, we're using this novel physics-infused neural network approach. And yeah, and we're doing this uncertainty quantification. So we're actually estimating the uncertainty of these estimates along the way. We're estimating all 5 of the FEE properties, and the other interesting aspect is we're validating this with simulation as well. So to the simulation a little bit, there's a couple of different methods that are used here. So a couple of different simulations that we've worked with initially started working with this kind of simplified 2D model of the bulldozer, and then moved to this more advanced compact track loader. The thing that's really important for the simulation is that we need to have it model the soil tool interaction semi-realistically. We're not trying to have it be an exact replica of the system, but it needs to have similar properties of the dynamics. And the other thing that's important is we really need to have some way of varying these soil conditions in the simulation of these V, C, and gamma parameters. And indeed, Vortex Studio, which is the software that's used to make these simulations, allows us to do that with changing different soil profiles of loam, clay, sand, and gravel, and additionally changing the compaction of the soil to collect data under different conditions. And this provides us with kind of these pseudo ground truth soil properties to use to test our system against. I call them pseudo ground truth because the simulation is kind of complex. It's got this discrete element modeling component as well. There's a number of heuristics that have been added based on operator feedback, so it's semi-empirical. And so the soil properties are one component that influences the forces of the simulation. So I guess the other thing is when we're performing these experiments, we measure a number of things. Again, we're measuring the position of the chassis and blade, the velocity of the blade, and in the more complex case, the positions of each of the joints with the compact track loader, as well as we're measuring this kind of blade force, which is what's depicted here in the red and blue. You can see it's kind of noisy, but on a real system, it's also going to be fairly noisy. So we want our system to be able to handle these types of issues. And then again, we're measuring the control and a local height map, either directly or by using LiDAR observations from the vehicle. Collect a data set across these 4 different soil types, and then we train our physics-infused neural network, which I'm going to describe next. So just to give an idea of what the inputs to this system are, we have observations from the vehicle. Those are those positions and velocities from the vehicle itself, as well as the control actions that are taken. And then we have this other set here, the theta k parameters, which are those known soil properties, kind of the geometric information that describes the FE, which can be extracted from a map. And I'll talk about that in the next section in a little bit more detail. So the output of this system is the soil property estimates themselves, this theta hat u, as well as the uncertainties in those estimates, this sigma theta u. And then the model also outputs a predicted force based on this interaction and an uncertainty in the force via that error propagation. So the way this works is that we have a couple of different layers in this neural network, a convolutional layer to kind of compress the dimensionality and time down a little bit, and then a transformer-based architecture in order to kind of pay attention to different parts of the sequence. And then this integration network is a fully connected component that combines the observational history with this kind of theta k, this geometric information from the FE, in order to produce the soil property estimates. Now, the physics-infused part of this network is this block here, this FFE. So this is that set of equations that I was showing you before. That's been embedded into the network itself so that the soil property estimates are fed to this system in order to produce this predicted force. Now, additionally, you notice we have this other error here, this F hat R, which is a residual force, which helps to account for the fact that the FE is really an approximation of this physics. And things like accelerations and some of those penetration forces are not modeled by the FE. And in order to keep to get accurate force predictions and not mess up our estimates of the soil properties, this allows us another method to kind of compensate for some of those unmodeled phenomena. So I'm going to briefly walk through this. We don't have to pay attention too much to the mathematical details here, but I'm going to kind of give an overview of how the system is trained because it's kind of essential in making it work. The main way that the system is trained at supervisory signal is this force prediction loss. So we're predicting a force and we're measuring the force, and then that's used to train the network via back propagation. Additionally, we have this regularization component to make sure that residual component that's helping to deal with those unmodeled dynamics stays small most of the time. It's not overpowering the rest of the FE model. But we have additional information that's available. We have information on the reasonable ranges for some of these properties. We know cohesion can't be below 0, and at maximum it goes up to 30,000 pascals. So that type of information from these real physical properties helps to constrain the network and produce better estimates. And then we have this other parameter that I didn't talk about, but is the residual parameters that allow us to make small adjustments for things like localization errors. If we don't know the depth of cut perfectly, we can allow the network to make these small corrections. We want to make sure that those are small. And then I guess another point to make here is that we're not doing this 3 to 8 dig cycles, but we're making multiple predictions even under that 1 second horizon. As the depth of cut is changing, we're making P predictions. So I think in this case, it's about 30 predictions. And that helps to kind of further constrain the problem a little bit. And then in order to do this estimation of the uncertainties, we're using a negative log likelihood loss that helps us to update this sigma theta parameter that back propagates through that error propagation math. So just kind of looking at this qualitatively, I guess to put a number on it, the force prediction error, depending on the model that's used, is somewhere on the order of 10 to 15% of the maximum force that the vehicle can exert. So this is kind of slightly better than other approaches in the literature. But what I want to highlight here is that the system is doing a fairly good job of making these force predictions. The dotted line here is the representative of the actual predictions, and then the solid red line is the measured force, and they're kind of on top of each other, if you can tell. And so the other thing to note is that these kind of shaded regions are indicating this uncertainty, this 1 sigma uncertainty in the predictions that are being made. And you can see that our predictions are within that the majority of the time. This graph is produced through the estimate of the soil properties themselves. I guess to kind of draw your attention to a couple of these, this bottom parameter phi is the internal angle of friction, which is one of the more important properties for determining the soil force. We're doing a fairly good job of estimating it. The green line is the true value. The blue line is this value of our estimate over the course of this rollout. And we're underestimating it slightly, but overall we're getting close to the correct value. C, you will notice, is another parameter that's very important, is the cohesion, and you can see we're overestimating this pretty substantially. But in reality, this actually ends up resulting in fairly good force predictions, which is interesting. Part of the issue is that when D is underestimated, C gets overestimated, so there's a little bit of an ambiguity in the model. It's not able to back out the difference between these two parameters. So some sort of other prior knowledge might be required to improve this. But in general, this is also reflective of the whole the simulation having additional heuristics that are unmodeled. So again, these are kind of pseudo ground truths. So you're taking with a grain of salt. But if we look at the data set in more aggregate form and look at these parameters over different compactions, so this bottom axis is as soil is increasing in density, so it becomes harder to dig at this end of the graph. And you'll notice that we have for the green dots, which is the ground truths, pseudo ground truth values are increasing with respect to compaction, internal angular friction and cohesion and density. And you'll notice that our estimates also increase with compaction. So that's a good sign that tells us we're extracting something meaningful through these estimates. So just to wrap up this section a little bit, we formulated a physics-infused based neural network approach, a novel approach for doing soil property estimation. It's fast and is applicable to bulldozing in particular because the bulldozer is moving around in the environment, not staying in one static location. Additionally, we've kind of come up with this new error propagation approach for estimating the uncertainty of these parameters using this negative log likelihood loss. And we validated this system in simulation, which to my knowledge has not been attempted before as well. And we've shown that the predictions are reasonably accurate and produce accurate force predictions as well. The other thing is that this system is extensible to the real world. This is done in simulation, but we don't really require estimates of the soil properties themselves to train the system. So we wouldn't have to have someone go out and make a bunch of lab tests in order to train this on the real system. We just require measurements of the force. And yeah, I guess the other thing to point out is this ambiguity in the model, which is something that hasn't really been pointed out in the literature before, but I think is a fundamental limitation of when you're trying to estimate all these soil properties. There's some ambiguity in the relationship between phi and c, for example, that is going to limit your ability to accurately estimate those without some other prior knowledge. So now that we have a way of estimating these soil properties, the question is, can we build a method to track them in some way spatially so we can see how they're changing over the environment? So this is recent work that's currently submitted for review and also at ISTBS. So just to give a quick overview of the approach here, we're using a multi-layered grid mapping solution. So kind of representing the terrain is in this XY grid with different layers. And in each location, we have, in this case, a height map, so we can represent the elevation. We have the ability to represent other quantities as well. The amount of loose soil that is located at a given location, we can change that and track that. Additionally, we can track the soil properties themselves as separate layers. And from those soil properties, we can compute these kind of strength measurements as well. That gives an indication of how hard it is to dig in a given region. And the way this works is that we're taking in observations of point clouds from a LiDAR or a depth sensor that is used to update the height map in this Bayesian manner, given the knowledge of the position of the vehicle. And then we additionally have this ability to do swept volume intersections to displace the soil. So we track the position of the blade as it's interacting with the terrain, and we can say there was an intersection here and we move that soil to a new location. Beyond that, we're then swelling the soil when those displacements occur, if it's compacted soil to begin with, and we're able to erode the soil so that it forms a more reasonable, realistic shape. So in that process, that allows us to extract these theta k parameters, the geometric configuration, and feed that to our soil property estimation network, which then allows us to have the estimates for that region of the terrain that's been interacted with, and we can apply those observations to the wedge of soil that corresponds to the FEE region. So yeah, and this is just a little bit of an illustration of what I mean by the swept volume. You can track the position of the blade over time and then intersect that with the height map. So what does this look like? Up here is, again, you can't see, but it says elevation map H. So this is the map of the height map of the terrain. So in this case, we had a small hill here. There was a cut through the terrain, and you can see that soil was kind of spilled off to the sides and built up on the front of the blade. I believe this is done without any of the LiDAR measurements in this case. So we're just assumed an initial terrain map and tracked the blade throughout this terrain. But additionally, we're tracking this loose soil thing. So by assuming the initial terrain is compact, then all of the movements that we make within that soil, we can say that when it's displaced, it becomes loosened, which is important for us to estimate that surcharge volumes, the amount of material that's built up on the front of the blade, which is important input to the FEE equations. Just to give an illustration of how this blind mapping or this tracking of the blade through the terrain works, the cameras or the point clouds can't actually see this region right in front of the blade. Operators can't see it either, but by tracking the position of that blade, we're able to kind of displace the height map as it's moving along. And we did some initial evaluations of how accurate this blind mapping is. This is an error plot showing the difference between the true value and the estimated value. And you'll see there's some discrepancies. Along the edges, we have some slight discrepancies where it's a little bit higher than it should be. The soil hasn't essentially spread out enough. This is really a reflection of not tuning the cohesion and the internal link of friction for the loose soil, which is not something that we're estimating because we don't know it yet. As we're interacting with the terrain, we can estimate it for the compact soil, but we don't know it for the loose soil. And so it needs to be kind of assumed in another way, or in this case, we assume it's the same across different soils. So you get slightly different behaviors, but this can be tuned to get better performance with the erosion, but it doesn't end up affecting the performance of the soil property estimation dramatically. So I mentioned that we want to try and extract these geometric parameters of the FE. Here, the way this works is that we kind of look at the intersection between the blade and this height map that's being built. In the region around that, we fit a plane essentially to that point, and then we're able to extract these geometric parameters by considering that plane to be the surface, and then looking at the angle of the blade with respect to that plane. So bringing that all together, what we can do is once we have these soil property estimates, we're fusing them to that region of the map that was just highlighted in the last slide, and then we're able to compute a soil strength measurement, and what we call here the FEE index. And the way this is done, these things are merged, is that we're using a Bayesian update. So using that uncertainty, so that in the cases where we make shallow cuts, if we make a deeper cut the next time around, or as we're moving forward, that we're able to kind of merge those estimates as the vehicle is moving through the terrain. But what we can do is we can take those soil properties, we can look at them individually if we want to, cohesion, phi, those types of things, but it's a little complex given the nonlinear relationship. And so what's more useful is to kind of come up with this soil strength index, or this FEE index, and where you're taking the soil properties and then assuming kind of a fixed geometric scenario and calculating the force that's required to shear the soil in that region. So in this experiment, we buried more dense terrain in this green strip in the middle, and then performed a number of passes with the compact track loader in simulation. And you can see that in this region here, that we're getting much higher forces. This FEE index, so indicating that it's harder to predict in this middle region. There's some discrepancies at the beginning of cuts. That's a known issue, and in particular, this is because we're kind of getting accelerations at this point, and so the actual uncertainties in those regions are higher as well. And then there's a little bit of discrepancies after we come out of this region, and this is really the hard region, and that's a kind of poor controller tuning in reality that results in some more accelerations and jittering that can cause some errors in estimation. But just to conclude this section, developed the first known method for doing soil property mapping at all, and then also doing this for a bulldozer. And what we're able to show is that there's a clear change in these soil conditions when we experience these kind of jumps in the difficulty to dig in a given region, the density. This physics-infused neural network approach that provides us with soil property estimates as well as the uncertainties allows us to do this kind of Bayesian mapping approach. and enabling fusion across state cycles. And we're using a GPU-based implementation, which allows this thing to run in real time. Again, the estimation is somewhat sensitive to the controller that was used. In some of the experiments, I tried to manually drive the system around without using the controller that was used to do the data collection, and we get worse performance. So that's something to look into, is collecting a broader data set that includes the different controllers. But in general, I think there's a need for some more thorough investigation of this multi-pass mapping, especially given the fact that we have layers in soil oftentimes. So as you're driving in a given region, it's not necessarily true that you're going to have the same soil properties as you get deeper. And so finding some way to kind of inflate the values with depth would be interesting to explore. Okay, so did a lot of work in simulation. Really wanted to get to the point where we could do some autonomous terrain shaping on real hardware. And so I'm going to show you some work from experiments here where we developed a map-assisted terrain smoothing controller. And what you're seeing here is a depiction of a berm that was created here at the Searle location. And the idea was, can we build a real compact track loader, and can we get it to perform some of these terrain shaping tasks? In this case, we focused on kind of an assisted teleoperation scenario, so not fully autonomous, but having the arm being controlled by a separate controller that's referencing the map. So just to give you a bit of an overview of what the system that we're working with is, calling this the Robotics for Engineer Operations Robotic Compact Track Loader, or the RIO RCTL for short. Somebody has a better name, I'll take it. But essentially, the system it's a compact track loader, so it has tracks, and it drives with a skid steer. It has a skid steer based drivetrain that's powered by a hydrostatic drive system. And additionally, it has this kind of 4 degree of freedom arm. So this is the loader arm. This allows us to control the pose of the blade with respect to the terrain. This first joint here is this Q1 joint is really an approximation of the actual kinematics of the system. In reality, this thing's a 4-bar linkage, but near the movement of operations for performing bulldozing operations, it can be approximated as a radial joint. And then the second joint here is this pitch axis. So the blade is able to kind of pitch up and down, which also affects the height of the blade off of the surface. And then the third axis is the blade roll. So you can actually change the roll side to side of the blade in order to deal with varying terrain rolls as well. And then the blade can be yawed to do kind of plowing operations, for example. I guess a couple of things are important there to mention. In comparison to a bulldozer, a compact track loader has a much higher center of gravity. And what this means is that the system is more prone to oscillations, particularly about the pitch axis. So as you're going over small bumps, the thing can rock back and forth, which just makes the control problem a little bit more challenging than on a actual bulldozer. So just to give a brief overview of the hardware modifications here, this is the actual physical RIO RCTL. There's been a number of sensors that have added to this system, included a proprioceptive sensors. So we have these string potentiometers that are measuring the extensions of the hydraulic cylinders, giving us feedback on the joints. We also have inertial measurement units. They provide a secondary observation of these joints, although they're not currently being used because they were too noisy. And we have, as far as the perception system goes, we have stereo cameras that are facing forward of the vehicle as well as the rear, provide us observations of the terrain as the vehicle is moving around. And a lot of the proprioceptive sensors, as well as the onboard vehicle diagnostics, use this CAN J1939 framework. We kind of chose that because it's really robust when we're running these long wires. And additionally, the system has a GPS that's used for ground truth measurements, not used in these tests currently. Long-range radios to enable communication between the ground station and the vehicle itself, and a number of modifications for safety, wireless emergency stops on the actual back of the vehicle in case something went rogue. And then we also kind of redone the power system for this as well. So it can be powered via the engine, which charges up the battery via the alternator, or we have a shore powering solution as well. So on the software end of things, the system is built on top of ROS2. And for those of you that are interested, we're using the Zeno middleware in order to enable this publisher-subscriber kind of distributed processing within the ROS system. We're using a real-time patch kernel that allows us to do more precise measurements and better CAN communication. And we've built a user interface for this using a platform called Foxglove. It's nice because it's reconfigurable. We can add in ROS topics fairly easily, write your own plugins, that type of thing. So what you're seeing here is kind of a version of that. We've got camera images from the vehicle that can be displayed to the operator. We're displaying the kind of a virtual CAD model of the vehicle, and that's changing as we're getting feedback from the positions of the joints. Getting some sort of diagnostic information as well, fuel levels, RPM, that kind of thing that's useful to the operators. And then additionally, we were able to display this terrain map, which is the result of the prior work in the prior section, and the vehicle position with respect to that terrain map. I guess the other thing to mention is that we actually implemented this on a handheld controller. So the operator actually has joysticks, kind of like a Nintendo Switch, if you've seen one of those before, that can actually drive the vehicle in that way. So, initially we focused on developing this smoothing controller. And the reason we chose that is because it allows us to perform a number of terrain shaping operations. It kind of fits under the purview of smoothing. Some of the tasks include things like material spreading. Can you spread out a pile of soil? Lane proofing, so a combat engineering application where you're supposed to cut down a specified depth in order to clear a lane through a minefield. Obstacle reduction, removal of berms. All these can kind of be formulated under this idea of smoothing. And as opposed to doing something like grade control, which is available on more of these OEM systems where you are trying to achieve some specific desired final profile, and the blade's used to track that desired profile. Here, we're formulating the objective locally. So we want to control the edge of the blade with respect to that local terrain map, and trying to smooth out the terrain in that local region. And the way that we do that is we fit a plane to the height map, this height map reference near the vehicle that's indicated in this kind of yellow box. And then that plane is fit to that, and we are able to extract the relative position posed to the blade with respect to that terrain. So we can get the relative height, we can get the inclination, the pitch of the blade, we can get the roll of the blade with respect to this terrain. And this is useful from a distributed control approach too, because we can extract these plane parameters, and then we can have our controller running at a higher rate elsewhere that's not relying on us having access to the map. And in order to do the actual smoothing operation, we need to be able to control this blade edge with respect to this plane. And the way this is accomplished is via this cascaded blade controller. And so at the low level, we have basically closed loop velocity control on each of the joints. So controlling that Q1 through Q4 joints, and these are tuned using a feed-forward PID controller. And it's important to note that the feed-forward component was really essential in making this work. What you're doing when you're sending these control commands out is you're changing the position of a hydraulic valve, which is changing the flow to the hydraulic actuators, which then changes the extension rate of the joints. So it's pretty proportional to the actual velocity. And we additionally made some modifications to deal with the fact that these systems have pretty intense joint limits. So it's a very, very small range of movements of some of these joints. And this ends up being important, especially if you want to add things like integral control, so that you're not, when you're backing off of these joints, that you're not lagging much. I guess, and then what feeds these joint commands, if you want to teleoperate the system, you can do velocity-based teleop. Or alternatively, if you want to enable the assist system, we're doing this joint, this kind of mixed joint and task space position controllers. So at one level, we're controlling the relative blade pose, the height and roll of the blade with respect to this terrain. And then at the other level, we're controlling individual joint positions. The pitch joint, we have a desired pitch position, as well as the yaw joint, which is not really used in this work. We're not doing a lot of plowing operations. But it's a little bit tricky in the sense that both the virtual lift arm axis, that first axis, changes the height of the blade, and so does the second joint, the pitch joint. So we're not doing a kind of advanced or an inverse kinematics approach here. We're really kind of using this weighting of different objectives for this Q2 axis. So we want when the vehicle hits its lower limit on that Q1 joint, which happens a lot during the bulldozing operations, you want to be able to still have control over the height, and we can use the pitch axis for that in that scenario. But when we're off that joint, we'd like to have our pitch to be set so that we're kind of achieving a good blade angle with respect to the terrain. And so this method to kind of mix these two objectives for the Q2 axis was developed. And I guess the other thing to mention is that the operator is providing these inputs. The operator is deciding how far do you want the blade to be off the ground? Do you want the blade to be rolled with respect to the existing terrain? Are you trying to make a new angled surface? And they have control over that by adjusting the joysticks. So did a couple of tests with this system. One is in this berm reduction test, which was done here at Searle. This is a scan from a Trumbull total station that was taken at this test area. Kind of got a D3 bulldozer there for size reference, but this berm is essentially 16 meters long. Before getting to the real world tests, we did testing in simulation. And then a second layer of testing and simulation was done where we actually built the ROS2 into the system to do the software in the loop testing to work through some of the bugs in communication. And then it was actually deployed on the real CTL. A novice operator was made to use this system, and he'd driven the vehicle before, but not had really experience driving using the assist system at all. And within he was trained in order to remove this berm. So basically told he knew what the joysticks did and was set free on the task. And he was able to sit in this trailer here performing beyond visual line of sight teleoperation, so had no direct view of the vehicle itself. And another thing to mention is that this test was performed the day after it downpoured at Searle, so the terrain was very wet. This is a loamy soil, so very cohesive, and it was very saturated, making it kind of a difficult task for the CTL. So this is pretty heavy soil and low traction. So where this will play. Okay, so what you're seeing here is kind of a quad view of the top left. We've got the user interface that the operator is seeing. Here's a view from the side of the vehicle performing an initial cut into this berm. And you can see that the arm is being controlled entirely by the assist system. And the operator is just controlling the movement of the tracks in this case. And so the coordination of all the different joints is being taken care of by the arm. And then you can kind of see what the operator sees. It's difficult to see the berm at all, even from an operator perspective. So having this ability to kind of track the pose of the blade with respect to the map, and I guess it is important. And you'll notice here we're doing a back dragging operation. So operator just reversed, and in that pass was actually able to smooth the terrain on the backwards direction a little bit as well. And also, I note this was sped up 2 times just for time here. So you have to drive pretty slow at this point. So I guess to give you a little bit of results on this test, a little bit more quantitative, this berm was successfully removed in about 20 minutes. I think this could have been shorter, on the second approach, given it was a novice operator. You can see here in this initial height map, the berm is significantly higher, and then in this final height map, which was scan performed afterwards, you can tell that the berm has been moved. It's difficult to see where it was at all. If we look at the difference between these 2 height maps, you can see that terrain is removed where the berm was at, and then it was spread out in this region to the left. And that was the result of mostly those initial pushes. There's a little bit of terrain that's spread out on the right as well, and that's the result of these back dragging operations. The other thing to note is that the final slope is fairly small as well. So what was computed here was the slope along this X direction. You can see it's higher on this side of the berm, low on this side of the berm. And then after the fact, it's difficult to see if there was a berm there at all. Maybe it's a little noisier because of kind of windrowing kind of behaviors with the CTL, but it looks pretty good. Another thing to mention is the operator got significantly better over the course of this. So initially, they were driving a little bit fast, perhaps, and it just takes time to use the system. And again, this comes back to the fact that the CTL is very, it has a lot of oscillations about this pitch axis. So, and additionally, the controllers themselves were tuned to have fairly good position tracking in a stationary state. And so when we go to start moving, there were cases where we get big steps and some oscillations would occur. And so there's improvements that could be made on the tuning side of things as well. But fundamentally, the control is really limited. These actuators, these valves themselves are very low bandwidth, coming off of the machine, something around 5 hertz. And additionally, the joints themselves are very high friction. So there's a lot of static friction, just the way that these couplings are made. And then, yeah, so this causes significant issues from a control perspective. And there's some latencies involved in the system as well. The other main issue that we ran into was the fact that the localization drifted throughout this process. So we weren't using GPS. This was done in a GPS denied fashion, but that gave us some headaches. So we were using a SLAM based approach to do localization, and additionally, so using these visual SLAM, RGBD SLAM from the stereo cameras that are on the vehicle. Some improvements were made since then in order to alleviate some of these problems, but some more work needs to be done in that area to make improvements there. I guess the other thing to mention is that teleoperation latency could cause some problems. So, if the camera images coming back were delayed, this made it difficult for the operator to make decisions. Interestingly enough, we were able to prioritize the movement of the feedback of the vehicle, so the operator could see the movement of the vehicle fairly accurately with respect to the terrain, and this helped to deal with some of those latency issues. And the other thing to mention is that the cameras were miscalibrated for this entire test. So during transport from Missouri back to Searle, at some point the cameras slipped, and we didn't realize that until later on in the test. And the system was still able to perform well just by the operator was able to make that height reference adjustment that enabled the smoothing controller to work well. So additionally, there was a test that was performed by actual trained heavy equipment operators. And this was part of the MISPICS 2025 experiment, maneuver support, sustainment, something, an army operation experiment. Wow. Yeah, I tried. I didn't want to put it all on the slide. Too many words. Anyway, so what the soldiers were trained to do is to perform. They're already trained to perform combat engineering tasks. What we did is we gave them this platform, showed them how to operate it, how to use the joystick, and they performed a number of combat engineering tasks. We had in mind this task of doing a kind of berm reduction. They had other ideas of things that they wanted to test, including some ditch filling tasks. And then at some point, they really wanted to push the system to see how far it could go, and did some tests resulting in double berms. These are tasks that they thought fairly new operators with less than a year of experience or so would have a challenge in performing. Oh, video should be playing, sorry. And they were able to perform, the smoothing controller was able to handle some of the coordination of the arm as the vehicle is moving over berms and trying to maintain that height set point fairly well. Number of things we learned from this. Everybody has different preferences in terms of the user interface, where they want a camera view versus where they want the map view, what size they want things. We're able to accommodate that with this Foxglove interface fairly well. They really found that terrain map display fairly useful to give them context on where to drive, for example, where it's hard to see from those camera images what's going on, especially if it's soil on soil. And so having that map was very useful for that purpose as well. They really preferred low latency over higher video resolutions. So we had to really back those down because they wanted the video feeds to come in as delayed, or least delayed as possible. Another thing they mentioned is they really would like audio feedback. And this comes back to how operators are using these pieces of equipment, is that sound is one of the other integral parts of this. You can hear when the blade touches the ground. You can hear when the engine revs up because the system's starting to stall. And another point to make, I guess, is that they really found the smoothing controller quite helpful. and we're able to essentially drive the system around with one thumb operating on one of these sticks, which is kind of indicating the ability of the system to maybe be used at higher levels of autonomy. And the other thing that we found interesting is that they really thought that this need to travel at low speeds was not very limiting. And then we're performing a lot of these operations that oftentimes you are traveling at low speeds anyway, just kind of the nature of the problem. So I think there's improvements that could be made there, but it wasn't a huge limiting factor. Yeah, so I guess what this showed is that we're able to validate this terrain mapping system in the real world with these blind mapping updates from the blade. We developed this novel smoothing controller that allowed us to perform some of these combat engineering tasks and demonstrated this on an actual bulldozer as well as in simulation. And again, I think there's still a need for adaptation to soil conditions here. That was obvious when we did this test at Searle, and the soil conditions were significantly different given the rain. We had to really change the height offset substantially in order to keep the vehicle from stalling, just because we had less traction and the soil was a lot heavier to move. So some sort of adaptation is necessary at the local level, not just at the planning level. This was actually implemented in some of the data collection of the soil property estimation methods, where in order to do automated data collection, the system was trying to track a desired forward velocity, and when that error increased, the height offset was also increased to accommodate, to keep the vehicle from stalling. So something like that could be possible, or something more advanced could be used as well. The other thing that I think would be valuable to help compensate for some of these pitch oscillations and the delays and control, the latencies and the low bandwidth control, is looking ahead in the terrain map in some way. And there's been some evidence in the literature that this type of approach is successful, where you're looking at where the vehicle is going to go and starting to compensate ahead of time. So just to kind of wrap things up and look at the research as a whole here. So, we started out by looking at this model learning and how do we learn dynamical systems of these complex processes of a blade interacting with the ground, and how can that be used for doing control. And the issue is that it was limited in application to we're using fairly simplified simulations, but weren't really considering the fact that soil properties change, and this really affects the earth moving process a lot. And so that motivated the use, the development of the soil property estimation system, which is a novel approach using these physics-infused neural networks. And first of our knowledge to be applicable really to bulldozing operations, where you're moving as you're traversing the terrain and performing these operations. And this was able to be tested and integrated with a mapping solution, where we're able to track these spatially varying soil properties and actually produce maps of them, indicating regions of higher difficulty to dig. And then components of this system, the mapping system, were implemented on a real platform. A real platform was brought up in order to begin studying these autonomous terrain shaping systems in the real world, and a smoothing controller was developed in order that aids operators from performing some terrain shaping operations. So there's a lot of potential in this field. There's a lot of future work. I'm interested in extending the soil property estimation to the real world. Now that we have kind of an actual platform to work with, there's still some limitations on instrumentation. And it's been difficult to get force sensors added on, or hydraulic pressure sensors added onto our vehicle due to procurement delays and that kind of thing. But hopefully we'll be able to start working on that in the near future. Improvements to localization would help make the system a lot more robust and not require us to reset the SLAM system, every 30 minutes or so. And I think there's a lot of potential for investigating, further work that's required to investigate these multiple earth moving cycles and how the terrain varies with depth, for example, and how to do that fusion properly. But overall, what we want to do is enable soil-aware terrain shaping, and I think there's a possibility of extending some of the model learning approaches that were initially attempted with now this extra information that we have, these soil property estimates, so that we can have the system that can reason more about these terrain interactions, knowing the physical characteristics of the soil themselves. And that allows us to make better predictions and to enable more accurate controls. And I guess what this leaves is really a question about how do we want to enable systems to do soil-aware autonomous terrain shaping. And I think what we've shown here is we've built up a number of tools to work towards this problem, and that I think that there's some clear ways of moving forward towards that. And I guess with that, I'd like to acknowledge all the support that I've received in this work. Big thanks to the Rio team for all the work, especially the hardware experiments would not have been possible without everyone's time, years of work. And I want to thank the HTA lab for supporting me through this journey as well, and all my friends and family. Thank you. I know it's been a long time coming, so I appreciate your patience. And with that, I guess I'll open up to questions.
Any questions from the audience? You can ask now. Maybe while folks are thinking. Ahmet, do you have any questions?
I do have a couple of questions. Hey, Jacob, it seems like a lot of the work that you have accomplished was done in simulations, but throughout your talk here, you highlight the fact that a lot of these simulations are inaccurate when it comes to soil modeling. So, what I'm interested in is to hear you talk about how we're going to bridge the gap going from simulation to real life and what can be done.
Yeah, that's fair. So a lot of the work was done in simulation, but I guess the focus in this was to think about simulation more as a tool, to consider it instead of a digital twin of the system that we're interested in developing, as opposed to kind of using these reinforcement learning methods where we assume very good models of our robot dogs and train policies in simulation, and then transfer them to the real world. Here it was used as a tool to kind of represent the type of physics that is going on, and to enable us to develop data efficient methods for solving some of these problems. So that was really important, is we wanted to be able to ensure that if it's not accurate, we can't rely on the sim to train a policy, for example, or a model. But what we can do is we can use it as a tool to say, can we get down the amount of data that we need in order to perform this learning test? That when we get on a real platform, they're kind of reducing the burden on the real data collection. So as far as how do we kind of bridge this gap between sim and the real world, I think the reducing the amount of making data efficient methods is important. There's some potential for doing more of this kind of domain randomization approach in simulation that some people have had success with, and building really simple simulations and then randomizing over soil properties and that kind of thing. I think that relies a little bit on having really good low-level controllers and kind of ignores some of the nonlinear dynamics, but could be successful. In general, I think that going down this route of collecting more results on real hardware is probably preferable, given this kind of gap that we have to overcome.
I got one more. I can go again. Okay, so I know you're aware that some of our team members here are already experimenting with feeding large language models a lot of data to enable complex robotic behaviors. And if you look at literature or some of the information coming through recently, there seems to be a lot of improvement happening in this area, to the point of some of these results start behaving like foundation models for some of those robotic systems. So knowing how complex what we're trying to accomplish within Rio, do you think there is a similar approach that could be taken for some of these combat engineer tasks?
Yeah, so I guess this is a new area of research for me. I've not spent a lot of time looking at the foundation models themselves, but I'm very interested. Especially people are showing pretty good generalization performance in some of these more household tasks where you've got a robot with 2 arms that's learning to fold clothes, and working in various environments. So I think it's really interesting and promising work. I think for one, they're relying on pretty large corpuses of data. So that's, again, a bit of a challenge, but I think that it's something that we could overcome. We've now got a platform that we can record human operators performing earthmoving operations. So I think I'm interested to see how that moves forward. Yeah, I think the other thing to mention is that the domains are a little bit different. A lot of this focus has been on, vehicles with robot arms. Technically, you can think of the CTL as a mobile manipulator, a base with an arm attached to it. I think that's an accurate description, except the applications that we're doing is we're kind of moving the terrain around. It's not quite the same as this kind of object level manipulations. And I think it also means that we need to think about different observation sources for these systems as well. So instead of just RGBD cameras, maybe it's useful to provide these systems with elevation maps or soil property maps. And I think in particular, because a lot of these terrain shaping tests are long horizon, and we're, as you're making a push with a bulldozer, you're moving, hundreds of feet, for example. And, that might not be visible in your single camera image or within the context window of some of these approaches. So having some other source of observation could be valuable in enabling that type of performance on these systems. So yeah, I'm interested to see where that goes.
Do you see any interesting applications for the use of your soil property maps outside of control?
Yeah, so I kind of heard that there are people that are interested kind of in the construction industry in understanding the properties of the soil before you're trying to put a building in some place. And oftentimes you're doing earthwork in this process. So, as you're performing some of those earthworks operations, if you're able to extract information about the terrain as an alternative to doing some sort of soil sampling, that could be an interesting application. I think there would need to be some work done in order to really improve the accuracy of the system if you're wanting these real absolute values of cohesion, internal angle friction. I think for this work, the accuracy of the properties is to some extent a secondary thing. We want them to be accurate, but mostly we want them to be representative of the forces that are going to be, required in order to shear the soil, because that's what matters for the terrain shaping objective. But if you really care about the true values of these things, I think additional information might be needed. So there's been some people that have been doing work in the area of estimating the granularity of soils based off of images, for example. And if you have some knowledge about the granularity, you can extract you can kind of assume things about how cohesive the soil is. And that could help improve the accuracy of one of these systems if you had additional kind of information to bias the estimate. But yeah, in terms of other things outside of the construction, I'm not sure. That's one of the areas that I'm aware of, though. Yeah.
Do you have to change the geometry of the blade for your second paper or first paper, moving into working with the compact track loader?
Yeah, it's a good point. So the first paper, we kind of assumed a flat blade, right? And in the second paper, the blade of the compact track loader is actually curved, and that's it's useful for cutting operations to have a little bit of that angle in it. But what that means is technically as you're going deeper cuts, the blade angle is changing if you're trying to approximate it. For right now, what was assumed was actually a fixed blade angle. So we allowed the simulation to proceed with this curved blade, but then we kind of fit a plane to the surface of the angled blade there. I think there could be some improvements made on feeding of those geometric parameters to the soil property estimation model. So if we know what our depth of cut is, for example, then you could come up with a better approximation of the blade surface for that curved region instead of over the entire curved region. But it didn't seem to cause too many problems in terms of the estimation accuracy. It's going to have slight differences in the mapping side as well, right? Right now, the mapping supports basically the use of these kind of polygon planar surfaces for displacing of material. But you could extend that by having multiple polygons, for example.
Slightly outside of scope, but you talked a little bit about having expert operators and novice operators, that kind of like gets a little bit into HMI field. And has there been any, or do you think it's worth looking into comparing performance with and without the online controller with expert and with novice operators, having some sort of quantitative results, or even feeding that into gathering data with expert operators and novice operators, and then feeding models and seeing the difference in performance?
Yeah, no, I think this is really interesting. I think I'd like to go in that space. I haven't focused on that right now to some extent because from the Army perspective, if it's getting somebody out of harm's way and it can do the task 50% of what a real operator could do, it still has value, right? But yeah, I think some more thorough analysis of some of these systems and how accurate, how efficient they're able to be would be interesting. I guess another kind of side point is that if we're moving towards some of these larger models, imitation learning based approaches, that kind of thing, it seems like people are having success in including demonstrations from both expert operators and people that are bad and novice operators. And the reason the way that I can understand that at this point is that you need to have examples of the system performing well so that you can recover and the system can learn to recover and perform operations a little better. It explores the space a little bit more as well of the system. But yeah, I think as we move forward to kind of future versions of this stuff, having some sort of more quantitative evaluation of the performance and using humans as a baseline is a good way to do that. And that's to some extent other people in the field that are doing like wheel loader scooping tests and that kind of thing. When you're doing it on like a mine site or some sort of rock loading test, that's an important metric, I guess. So yeah, I'd like to move in that direction as well. Maybe getting some actual heavy equipment operators from down at the engineer school, for example. Yeah.
Earlier presentation, you were talking about you have like a 61 by 101 space, your RT space.
Yeah.
How did you come up with that number for your 6 by 10 grid? And is there any consideration of changing the size of your grid spaces and doing a cascade of operations, so saying like 1 meter squares and half meter, 10th meter, and see out of that you can see better?
Yeah. So I guess that was with respect to the model learning work. And I was trying to mimic some of the methods that people used in that space. So like the world models approach, they were originally taking RGB image data from, I think, the Doom video game or something like that. And so what I did is I modified it so, height maps kind of look like images. So I wanted it just a kind of regular grid. I would say that to some extent there was an arbitrary decision on the resolution. I wanted it to kind of not have too many gaps. But yeah, I think especially as you start thinking about what level of planning you're doing, having different layers of granularity of these observations, both for of the height maps and maybe of the soil property maps. So matter. So at higher levels of planning, when you're doing these strategic plans and trying to organize multiple dig cycles, maybe it's enough to know that this place you can't dig and this place you can dig, versus when you're doing that kind of lower levels of planning and control, that you really want to have a finer grain knowledge of the forces that are going to be required in order to perform a given operation. But yeah, no, I think kind of having multiple granularities data could help, and maybe potentially allowing it to have larger maps, a coarser granularity. And that's something we ran into in the teleop as well. We reduced the granularity of the maps so that it would stream over the network better. But I think it could have had some impacts on the performance of the smoothing controller a little bit. Some of those things are things that could be solved with like compression stuff. But yeah, no, I think that's an interesting idea to maybe include different levels of granularity in model learning.
And I think we'll pause audience questions. Audience, you can ask questions when the committee's deliberating. So we'll switch to questions from the committee. Kris, do you want to go next?
Sure. A couple of observations that you made from your teleop experiments were that, I guess, one, the operators wanted audio, and two, the slippage in your earlier experiments of the tracks was one of the signals that you could use to kind of decide on the cutting height. And it seemed like, so your earlier work did not, well, your work in your thesis did not use these two sources of information to, help guide the decision making. So in future work, how would you potentially use, let's say, audio as a proxy for a force sensor, or use traction to help estimate these terrain properties?
Yeah, so I guess I'll start with the traction one. Uh, there are other models of the physics between the interaction of tracks and the ground. They kind of, you described it as like, especially in systems that have grousers, you can kind of model the shear forces of the tracks interacting with the ground there. That was one of the things that I was interested in potentially adding as another set of physics that you could build into the system as well. And it does require you to kind of have some estimate of track slip. So right now we have a SLAM system that's giving our localization solution. We also have the ability to measure the track speeds. So I think we would be able to derive some estimate of track slip there and use that with additional physics in order to inform the soil property estimation. As far as the sound goes, I think that you could use. So I'm not that familiar with like networks to do audio processing stuff, but I know that's there's different methods that people use to break things down into, using Fourier transforms and that kind of stuff, have some sort of frequency-based representation of the data, and potentially feed that in as another set of observations to that initial part of the network, similar to the position and velocity information. So you could kind of just use it as another set of features. But yeah, we also have access to RPM, and I think that for a large part, the RPM is a good analog for like the sound of the engine itself. So that could be kind of a single value feature that we could extract. As far as like the blade contacting the ground and that kind of thing, we have some idea of when that happens from the mapping system as well. But it'd be, for sure if you hear the audio feedback. So I'm not sure exactly how to incorporate it, other than maybe providing that information as another feature, perhaps.
I guess another question here is that you're estimating these material properties for certain cells that you're currently touching, right? But if you look at let's say some sort of site, and I find that the material behaves some way in my first interactions in some corner of it, generally speaking, there's some correlations of that information to the rest of the site. But currently, you have to touch the entire site to be able to build a map of it. So, have you thought of any methods that you would use to help, let's say, distribute or disseminate the information from a certain region to the rest of the site?
Yeah, I was kind of very interested in some of the work out of your group using Gaussian processes to model the kind of distribution of properties through a digging cycle. I think that's one way that you could approach this. So some of the kind of earlier like elevation mapping work, they were looking really at uncertainties in height observations, that kind of thing. But when you do this error propagation of the observation, you kind of come up with some sort of, in this case, a Gaussian distribution that describes, where to apply these values to. And then you, based on that kind of confidence, you can apply the Bayesian updates to subsets of the cells around these distributions. I think doing something like that would be valuable. And, it'd be interesting to try and correlate that somehow with visual information as well. If you got ground cover or whatever, then grass and stuff growing, it might be difficult to infer much. But if you've kind of got bare soil, the different colors in the soil properties could be valuable information as well, and determining maybe where to apply those updates to. I thought about applying them just to a spatial region around the vehicle, but with less certainty. You can apply the updates to the entire map from a single set point, and then as you got closer to the region, I think you could apply those Bayesian updates fairly well. And given the kind of way this thing's implemented is this GPU-based method, I think that could be done fairly quickly in parallel. But yeah, I guess that you're right. That's something that I'd like to explore as well, because the challenge though is that you get to scenarios where you've got hard boundaries between things. So if you've got a buried object or a tree root or that kind of thing, it's hard to make inferences. I think that in a lot of cases you probably can, but in some cases they're going to be inaccurate until you go and touch the ground there. But I guess that's the only way to learn really though, unless you do some sort of other method of observing underground terrain with GPR or something like that.
Good. I guess my last question is kind of dovetailing off of something that Ahmet mentioned, which is real data. So supposing that you wanted to drastically boost the amount of real data that you would be using to train various models, what types of instrumentation and let's say site prep or procedures might you need in order to either in a supervised or self-supervised way gather large amounts of data for construction?
Yeah, so you're saying without a human operator doing some sort of like RL based thing or with a human
Well,
operator?
with or without, what would be a kind of what would be your most, I guess, promising approach for gathering, let's say, hundreds of hours of interaction data with one of these
Yeah.
construction machines?
So I guess I'll tell you what our short-term plans are, which was currently for a couple hours a week sending one person on the engineering team out to perform operations in this drill site. That's pretty limited, right? And that right now we only have one type of material there. A lot of us aren't trained operators. As far as the instrumentation and stuff goes, in order to enable this, one, I think the system needs to be a little bit more robust, so that we're not debugging stuff as we're trying to record data. The localization system in particular could use some improvements. We have some future methods that we're potentially going to use to get better localization. We have the kind of the system that's developed in concert with Tremble that has a scan or the laser tracking total station that can sit off to the side and give observations of the vehicle position. So we're looking at integrating that as part of the system as well to have a better ground truth, because GPS, we have issues even when we have RTK GPS, we have GPS outages and things are kind of finicky. But yeah, so having that set up as a site to provide ground truth observations. I think we're going to also, one of the things that we're interested in doing is that a lot of these approaches seem to be using external reference cameras as well, not just eco-centric videos. And so having some sort of site camera that's integrated into the system would be valuable as well to make it better. I guess some of the things that we're interested in doing is if you've got an operator in there, in order to enable this data collection, having some sort of audio logging from within the cab, so an operator can describe in words what the operations that they're performing. Having some of the buttons on the joysticks mapped to beginning of data collection cycles, have some sort of display perhaps that's showing when an episode is being recorded, and to kind of give the operator some feedback that they push the right button, for example, to try and make this a little bit less of a 5-person effort to get data recorded and maybe 1 or 2. So I think some streamlining that whole process would be beneficial. But yeah, and it probably needs to be portable. All of this probably needs to be portable because we want to take it to other sites where the terrain is varying, the kind of visual observations are varying, and maybe taking it to a place down in Missouri where we've got trained equipment operator that we can give this thing to for a week or 2 or whatever. But yeah, I guess those would be some of the things off the top of my head.
That's all.
Thanks. Joohyung?
Yep. It's amazing to see actual implementation here. So I have a question about the interface in slide 39 or
Okay, let me pull it up and share the screen again. You said 39?
I think so. The video clip. Yeah,
Yeah, let me share it again.
sure.
Maybe. Screen 2. Okay.
Oh, not this one. The previous one, I think.
Previous one.
38.
Yep.
Yeah, this one. Could you
Play the
play
video?
it again?
Yeah. Yeah, sure. Maybe I'll mute it so I can talk. Oh gosh, trying to look behind me as I'm. Okay.
Uh, let's see. So in
Want me to pause it?
in this video,
Yeah.
I was wondering if you are using some kind of gravity direction. So in the display
Yeah.
left top one, the
Yeah. Oh yeah.
orientation of the
Yeah. So are you talking about this frame here where the bulldozer's
yeah.
kind of pitching? Yeah. We have so the reference frame is fixed to the orientation of the vehicle in this case,
Uh,
which is not ideal. We have another method. We had to implement a frame publisher that kind of pulled out the pitch of the vehicle. And that was just not shown in this test. But yeah, the terrain. So the terrain looks like it's pitching. Is
right.
as you're driving through it. That's something that we had implemented for the operators with a blade view at some point as well that they found to some extent useful. So you could kind of view the real world kind of roll and pitch of the blade. But
I
yeah, I
see.
think that's
I
needed
see.
here.
I see.
It's a little confusing.
I see. So in the well, I am very curious about some system details. So when I just briefly read the paper, you at least use three computers for this system, right?
Yeah, correct.
So
Yeah. So yeah, why are we using three? Is that the
no
question?
no no. I know why you
Okay.
need the computers, but my question is so did you use all like artifetch ones for all three computers? So one for the camera Jetson and the two are just identical like
Yeah.
computers. One for
Yeah.
future planning, one for current like implementation, right?
Yes, yeah. So yeah, one of them's more future proofing. It does a little bit of work. I think the diagnostic computer right now actually interfaces with the onboard vehicle J1939 port to get some of the information on the RPM and that kind of thing, feedback on the vehicle. But yeah, that's basically it's all it's used for right now. It's kind of planned for future operations. But that one was running a real-time patched kernel I think it was a server version of Ubuntu 2204. And then the other computer, the control computer, was also running a real-time patched version. And we did some initial tests with and without the real-time patching, and I think we got more consistent, latency performance, in terms of like threading and that kind of stuff at the kernel level. And we had some advice from one of the other people in the lab that had done some of this work and said that that was important for doing good CAN communications and avoiding like dropped packets and that kind of thing. And so that
I
was one of
see.
the
I
main
see.
reasons that we did it. I don't know that it's entirely necessary, but it seemed we had stable performance of the system. The Jetson computer I don't believe was real-time patched. It was using firmware that was provided by the manufacturer
Yeah,
of the
yeah.
computer. Yeah,
You needed that for the jet camera.
the Z cameras. Yeah, and we tried using at the hardware level. We tried using some nicer Z cameras, the GMSL2 connection ones, but had all kinds of difficulty with firmware and ended up reverting back to the USB based ones, which are not ideal, and we have power issues with and that kind of thing. But hoping with some firmware corrections, we can use the GMSL ones in the
I
future.
see.
Yeah.
Okay. And for the future, like system level, like direction, are you considering to make some kind of haptic kind of interface for the users or?
Yeah, so I think for doing the like recording of operator data and that kind of stuff, I think
Right.
initially we're thinking, oh, sorry, go ahead.
No, 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 no.
Oh,
Just keep going.
Yeah, so I'm thinking we're going to do a lot of in-cab kind of recording. So the operators are just very familiar with that setup. We don't have to think about video latency kind of stuff affecting things. I think that in the end, we're really wanting to move more towards autonomy as much as possible. So teleoperation was the focus of this kind of initial implementation. And I think it's still going to be a part of any application in the future. Like we're going to need to be able to teleoperate these machines to perform operations that are maybe not yet automated, but really kind of wanting to push towards automation. So I think the focus moving forward is less on the kind of user interface for teleoperation and more on maybe the user interface and development of how do you kind of specify the goals of the system. Where do you want to put a berm? Where do you want to reduce an object? That kind of thing. And so I think that the haptic feedback is maybe not as essential for those tasks. But there's also some work, I think it was out of Queensland again, where somebody did some teleoperation studies. And I think that they were indicating that haptic feedback for the earth moving stuff was not as important especially as audio feedback. I think I can't remember if they had a chair that moved with the vehicle as well. But I think having good joysticks, I think, is important. The joysticks on that controller are really awful. And the way that we had it set up is you were kind of having to hold the joystick in place to maintain a forward velocity, which is not really how it works on the Bulldozer. It is how it works on the CTL, but your thumb starts cramping up and that kind of thing. So a different user interface there would be valuable. But I think haptic feedback could be useful, especially maybe if we're trying to indicate something about maybe this is a harder region to dig or something, maybe not just like vibration of the machine or something like that, but some other additional information that would be difficult to ascertain from the cameras or something like that.
I see. So you think it's more important to collect a little bit higher level, like user data?
Yeah, well, no, as far as doing the user data collection, yeah, I think it's important to get good, accurate measurements of their joystick movements. But if you're trying to improve teleoperation performance, that haptic feedback itself, I don't know enough about it, but my understanding is it's not as valuable as other modalities like adding in audio and that kind of thing.
Let's see. Yep. That's it. Thank you.
Yep.